Hello, welcome back, and thanks for clicking on this Unarculus production. Today we are going to talk about implicit differentiation for the first time. Okay, so the first thing we have to do is we have to discuss what the difference is between an implicit function or an explicit graph. Okay, implicit versus explicit. So if you look down at the bottom here, we have two graphs, right? Two equations. Okay, the first one you can see is solved for y, right? It says y equals, it's y written in terms of x. Now this is the way we write most of the things that we've written in our mathematical lives, right? Through all the through the 11, 12 years that we've been doing this. And then we have another graph down here, x squared minus xy plus y squared equals 7. Okay, that is not written in terms of y or in terms of x, right? It's not solved for y. Okay, so what we have here is this function on the left we would consider to be explicit. Okay, explicit. It's explicit. It's solved for y and written in terms of x. Okay, the other function is said to be implicit. So, CIT, right? Yeah. Okay. Yeah, we'll do that. That makes it look better. All right, so that's an implicit function here on the right. This function is written in terms of more than one variable. Okay, so it's not solved for x, it's not solved for y, it's not y in terms of x. Okay, it's not even x in terms of y. So what we need to learn to do is we know how to derive something that looks like this, right? We've been doing it for like the last 2 weeks. The question is, how do you derive something like this? Especially if you can see here with this example, this graph or equation is not easy to solve for y. So it's not easy to take this and write it in this form, okay, with a y equals on it. So the question is, how would you derive something that looks like this? And that's what we're going to discuss here in this section. So to start things off, what we're going to do is we are going to derive some things that you already should kind of know how to derive. Okay, so the D, capital D, means we're going to derive. All right, so let's do some of these here. We have A, B, and C. Okay, and then there's a few more on the next page. I want you to derive for me x times f of x. Okay, so this is a product rule problem, right? It's x times something else with an x. So to use the product rule, we would leave the first, derive the second. Let's just do it. So we're going to leave the first, leave the x. Okay, the derivative of f is f prime x, plus leave the second, which is f of x, and derive the first, the derivative of x is a 1. So we get an answer of x f prime x plus f of x. Okay, that would be the derivative of x times f of x. All right, let's try letter B. I want you to derive f of x quantity cubed. Okay, so the derivative of f of x cubed, this is blah cubed. So we're going to use the power rule first, bring the 3 down, leave the blah, take 1 from the power, now it's the power 2. Now we're going to cross this out, and then we're going to have to derive f of x next to it. So that's then going to give me 3 f of x squared times the derivative of f of x is just f prime x. Come back up here, cross out f of x. We're done deriving, so this must be my answer. Okay, this is my answer to the first one. All right, let's go for letter C. It wants you to derive sine of x plus f of x. Okay, so this is another issue where you're going to have some kind of chain rule problem, right? Because you have sine blah, right? Sine is the outer function. So the derivative of sine of something would be cosine of that thing. So it's cosine x plus f of x. Okay, cross out sine. Times, then we're going to have to derive the x plus f of x. All right, so that's going to give me cosine x plus f of x. Let's see if I can fit it. Times the derivative of x plus f of x. Well, these are added, so the derivative of x is a 1. The derivative of f of x is f prime x. And if I come back over here, I cross this out, I just derived it. So I'm done deriving. This must be my answer for the third one. All right. So these are three things that look complicated, right? Three equations that look complicated, but you do know how to derive them. Okay. You have learned how to derive them in one way or another. All right. Let's look at a couple more. Okay. And then we're going to get into what it means to derive things implicitly. So the next one, they want you to derive tangent of f of x. Okay, so this is a tan blah problem, right? Tan is on the outside. The derivative of tangent of something is secant squared of the something. Okay, cross this out. Times, I'm going to have to derive f of x next to it. The derivative of f of x is just f prime x. So I get secant squared f of x times f prime x. Okay, here's my answer for that one. Cross this out, I'm done deriving. And then finally, letter E, the derivative of 3 f of x quantity squared. So the 3 I just leave. I don't do anything with it, right? Just leave it there. And I'm going to derive f of x squared. That's something squared. Its derivative is 2. Leave the something. Take 1 from the power. Okay, cross this out. This 3 doesn't do anything. It just sits there. And then I'm going to have to derive f of x next to it. The derivative of f of x is f prime. So we have 6 f of x times f prime x. Cross this out, and you're all done. Okay, there's your derivative for the last one. Now, why did we ever derive things that look like this? It seems pretty silly to do it, right? Because if you look back a few pages or you remember back, the functions that were defined implicitly were things like x squared minus xy plus y squared equals 7, right? I mean, they don't look anything like this, but if you think about it, they actually kind of do, right? Because y, another name for y, is f of x, right? So this thing really looks or could be theoretically written, oops, like that, okay? It could be written like that. Now these, wait a minute, we just did some of these a few minutes ago, okay? We just derived them. So that's why we derive these things that are up here. All right, they're things that you already should know how to derive, and they'll help us to be able to derive implicitly. Okay, all right, so now what's the issue then? So I guess the first question is, why wouldn't we just use f of x all the time? Just use f of x embedded in the function. Well, and again, the issue is we love to use function notation, right? We love to talk about functions. Okay, you've talked about functions for pretty much 12 years of your mathematical life in some way or another. All right, but you do have to understand that not every curve is a function. Okay, and if something's not a function, you can't use function notation. You can't use f of x. All right, you can't use f of x. So writing something like this would be great. X squared plus f of x squared equals 16. That would be amazing, except if you swap out the x or the f of x for a y, you get x squared plus y squared equals 16, which you should recognize, hopefully from shapes class, as a circle centered at the origin with radius 4, right? That's not a function. It doesn't pass the vertical line test. So this notation that we have here, although as wonderful as it is, and maybe as easy as it would make it for us to derive because we already kind of know what to do, you can't use it, okay? Because you have something that's just not a function. So you can't use function notation on a graph that is not a function. It doesn't pass the vertical line test. So this notation is necessary here. Okay, the Leibniz notation is necessary to be able to continue. All right, so now the question is, how do you derive this if you're going to work with Leibniz notation? All right, if you're going to work with Leibniz notation. Well, what we're actually going to do first is we're actually going to do this without Leibniz notation. Okay, we're going to do it as if you could derive this. All right, we're going to do it as if you could derive this. Well, how would we do this? Okay, we would derive each one of these terms, right? 1, 2, 3, because these two are added, and then we'd have to derive on the other side. If we derive on the left side, we have to derive on the right side of an equation. That should make sense to you. Whatever you do on one side of an equation, you should do on the other. Okay, and we've been doing that throughout, right? So just so that we understand, if I ask you to derive f of x equals x squared, you are deriving on both sides of this equation, right? On the right-hand side, you're getting 2x. But on the left, the derivative of f of x is f prime x. Okay, so you are actually deriving on both sides of an explicit equation like this one is. But the question is, how do we derive this equation that's implicit? I know some of you are laughing at me now because I just erased this. Yeah, I know. Yep, have a good time. Hope you got a good laugh out of that. All right, so how do we derive this? Well, again, you're going to derive each side. So these two on this side are added. So we just derive them separate because they're added. So the derivative of x squared is a 2x, just like it's always been. The derivative of f of x squared, well, that would mean bring the 2 down, leave the f of x there, times, cross this out. Then I'm going to have to derive f of x, right, the inside. The derivative of f of x is f prime x. And then over here, the derivative of 16 is nothing. It's just a number. So now the question is, could you solve this for f prime of x? Well, sure you could, right? You just got to get f prime of x by itself. It's like a variable. So I would subtract 2x on both sides. I'd have 2f of x times f prime x equals negative 2x. And divide both sides by 2f of x. And I would get f prime x is equal to, 2's cross out, negative x over f of x. Right? And that would be your answer. That's what f prime is equal to. Okay? But again, that would be all well and good if you could use function notation f of x. But you can't use f of x. You have to use y instead. So the question is, how do we do this with a y instead of it? Okay? Basically, we are going to do the same thing that we just did a moment ago. Except we're going to do it now with y. We're going to derive each term, term by term. Derive each side of the equations and derive by term. So the derivative of x squared is a 2x. The derivative of y squared. Now, look at what we did over here. When we derived f of x quantity squared, okay, the derivative was, well, we used the power rule, bring the 2 down, leave the blah, and then we derived the inside, right? Y is the inside. But we can't use function notation. We can't use Newton's notation and just write 2f of x times f prime x. We have to use Leibniz notation, so we're going to write 2y dy dx. The derivative of y, the rules apply to x's. The problem is this isn't solved for y. So that's why we're putting the dy dx in the middle of the problem here. Okay? And then the derivative of 16 is 0. And now you're going to solve for dy dx. So subtract the 2x on both sides. You'll have 2y dy dx equals negative 2x. And then divide by 2y. And you get negative x over y, which is the same thing we got up here, except it was in function notation. Okay? All right. So let's see if we can kind of summarize what we have so far. This is actually a pretty simple process once you get the hang of it. And the nice part about it is it's like a cookbook. You just do the same thing every time. So to do implicit differentiation, you're going to derive each side of the equation term by term. Okay? Number 2, when you derive a term that has a y in it, you're going to need to multiply by dy dx. That's the chain rule coming into play. Okay, that's the chain rule coming into play, but normally we would have written it as f of x, 2 f of x times f prime x, right? So instead, if we wrote y squared, its derivative would be 2y dy dx. Same thing. These two are exactly the same, except this one's in function notation, this one's not. Okay? They mean the same thing. All right? And then once you derive each term that has a y in it, you need a dy dx. Finally, you solve the equation for dy dx because that's the derivative. Okay, you want to get dy dx by itself. It's all algebra once you do the line 2. It's all algebra once you get through line 2. All right, so we're going to try some of these. Okay, I'll give you some hints as we go along that might help some of you. Oh, here it is, x squared plus y squared equals 16. All right, so let's try this one more time. I didn't realize it was here on the slide, but that's okay. All right, so here's what I would do if I were you, because this will help some of you. We're going to derive each term by term. Okay, so the derivative of x squared is a 2x. So now the derivative of y squared, and some people don't immediately see what to write. So if you don't see what to write and it doesn't make sense to you, come over here on the side. Now you're not allowed to use this notation in your answer, but over on the side it might help you. So how would I derive f of x squared? Well, that's 2 f of x times, cross this out, f prime x. Right? Cross this out, I'm done. That's what I would get, 2 f of x times f prime x. Okay, so then in y notation, the derivative of y squared would be 2y, and then I derived a term that has a y in it. I need a dy dx next to it. Okay, that's multiplied by it. Derivative of y squared is 2y. I derived a term with a y in it. I need a dy dx. And the derivative of 16 is nothing. So now I'm going to solve this for dy dx. Subtract the 2x on both sides. All right, we've done this before, but then divide by 2y. Dy dx is equal to negative x over y. And there's your answer. Okay, so at the beginning, some of you may have a hard time with understanding, hey, well, what's this y doing here? How do I derive it with this y? Look, just come over off to the side and use function notation, and it should become clearer as to what you should write when you go into the next line. Okay, all right, let's try a few more. Here's another one. It wants you to derive this mess. Okay, so let's derive this mess. You're going to derive it term by term, one term at a time, because everything's added and subtracted, right? And you got to derive on both sides because it's an equation. So let's start with y to the 4th. All right, so let's come over here. For those of you who might have a hard time, we're going to write f of x to the 4th. Okay, how does it work? Bring the 4 down, leave the f of x, take 1 from the power, then derive the inside f prime x. All right, so now over here, the derivative of y to the 4th. Here's how it works if you're going to do it without that. Derivative of y to the 4th. Just going to derive it, 4y cubed. But then you derive the term with a y, so you need a dy dx, because y is the dependent variable. Okay, plus, all right, now x times y. Well, that looks like this, x f of x, if I were to do it over here. That's a product rule problem, right? It's two variables multiplied. It's a product rule problem. You leave the first one, derive the second, plus leave the second one, derive the first. Oops, derivative of x is a 1. Okay, so over here, same thing. Leave the first, derive the second. The derivative of y is dy dx, right? Where the derivative of y is 1, and then you derive the y with it, so you need a dy dx. Okay? Plus, leave the y, the derivative of x is 1. And that's exactly what you got over here, isn't it? X, f prime x, x dy dx, plus f of x, y, times 1. Same thing. Equals the derivative of x cubed, 3x squared. The derivative of x, 1. The derivative of pi, pi's a number in this class, 0. So now you need to solve for dy dx. Keep everything that has a dy dx on the left side together, or bring it all to one side, and move anything that does not have a dy dx over to the other side. So that's 3x squared minus 1 minus y. And now you're going to factor out the GCF on the left. The GCF is dy dx. Factor it out, and then you can divide by what's inside. So we can divide both sides by 4y cubed plus x. And we get dy dx is equal to 3x squared minus 1 minus y over 4y cubed plus x. And that's the correct answer. Okay? And your answer is going to be in terms of both x and y, because so was the equation, right? And again, just so that we're clear, you cannot use this notation to write your answer, because there's no guarantee that what's up here is a function. If it's not a function, and you're using function notation, that's wrong. Okay? So let's keep going. Let's see what else we have. We have a few more, I think. All right, so let's try this one. Sine of x plus y equals x plus cosine y minus 5. Okay, so over here, if you're going to do it with the function notation, it would be sine of x plus f of x. So then how would you do that? Well, we did this earlier. Derivative of sine of something is cosine something. Okay, times. Then I'd have to derive the inside. I'd have to derive x plus f of x. So its derivative would be a 1 plus f prime x. And I cross this out because I derived it. That would be my derivative. So let's come over here and see how it works if you're going to do it with Leibniz notation. The derivative of sine something is cosine something. Okay, times. Now you're going to derive the inside. The derivative of x is 1. The derivative of y is 1, but you derive the y, so you need a dy dx. And that's all done, right? Same thing. We got the same thing over here, right, as we did here. The derivative of x is a 1. The derivative of cosine y, well, derivative of the inside is minus sine y times, then you have to derive the inside. The derivative of y is dy dx minus the derivative of 5 is nothing. That's the most common mistake. People forget that the derivative of the numbers is 0. They drop out. All right, if it's just a number by itself. Okay, so now this needs to be solved for dy dx. This is an algebraic disaster, but it's not as bad as it looks. Okay, if you distribute this to both of these, then you can gather your dy dx terms on one side and anything that doesn't have a dy dx on the other. So if we do that, we have cosine x plus y plus cosine x plus y dy dx equals 1 minus sine y dy dx. Okay. Bring your dy dx terms to one side, anything that doesn't have a dy dx to the other. So I'm going to bring my dy dx terms to the left. I tend to do that, but there's no rhyme or reason for it. You don't have to do it that way. And cosine xy gets subtracted over, so we have 1 minus cosine x plus y. And then I can factor out the dy dx, and then I can divide. Okay, so we have this, x plus y, and then we can divide both sides. We'll divide by cosine x plus y plus sine y, and there's your answer for dy dx. That's the derivative. Okay, that's your derivative. All right, let's keep going. Okay, here we go. I think this is our last one. It's x squared plus y squared equals 25. Now they want you to find the second derivative. All right, so we got to find the first derivative first. All right, so let's do this one without the notation over here on the side. I'm sure we can do it. The derivative of x squared is 2x. The derivative of y squared is 2y. You derive the y, you need to dy dx. The derivative of 25 is nothing. So now we're going to solve this for dy dx. It's easy to solve. We've solved it like 3 times now, right? This is the third time we're solving this. Divide by 2y. You get dy dx is equal to negative 2x divided by 2y, or negative xy. Okay, now I want to derive dy dx equals negative xy. All right, so what I'm going to do is I'm going to take the negative, and I'm actually going to put it in the numerator just to put it somewhere, have a place for it, because I don't want it floating out in space, because I tend to forget when it floats out in space there. So I'm going to put it with the x in the numerator, just that it has a place to be. All right. Okay, so here we go. Now we're going to go find the second derivative. So the derivative of dy dx is the second derivative. Now we're going to derive this with the quotient rule, right? I mean, this really says negative x divided by f of x. So we're going to use the quotient rule on this. That's ho d high. The derivative of negative x is negative 1 minus high d ho. The derivative of y is 1, but you derive the y, dy dx, over y squared. Okay? Now, the goal is to write your answer in terms of x and y. They're not going to accept an answer for d squared y dx squared that has a dy dx in it. They don't want that. So what we can do to get rid of the dy dx is we know what dy dx is actually equal to. We know dy dx is equal to negative x plus y. We just did it right here, right? So we could take that and toss it in there over y squared. But now we have to clean this up because now we have a fraction in the numerator. So we're going to have negative y minus x squared over y all over y. So we need a common denominator in the numerator. That's y. So the first term will need a y. The second term does not. So it's going to become negative y squared minus x squared all over y over y. So that would just be negative y squared minus x squared, over y divided by y. So keep this, change this, and flip this over. You'd have negative y squared minus x squared over y times 1 over y, which is negative y squared minus x squared over y squared. Now, you can get even fancier and go one step further, which they occasionally do. There's a GCF in the numerator. You can take out negative 1. If you do, you get y squared plus x squared over y squared. And then what they do is they go one step further because y squared plus x squared, you know what it is. It's 25 because that's the equation that we started with right up here. So they write that the second derivative is actually equal to negative 25 over y squared. Okay? And that's how you would find a second derivative. When you find the second derivative, if you get another contribution of dy dx, well, you take whatever dy dx is and you plug it in for where dy dx was. Okay? And that's, I think, all there is. Let me just check and make sure. And that's it. We did it. All right? That's it for today. Thanks for clicking.